Hi class, for these applications what we're going to be doing is evaluating integrals, and in this case definite integrals. What they're going to represent is going to be areas under the curve. So what the integrals are going to be technically evaluating is technically the total area that happens to be below the curve or technically above the curve. So it all depends on how the problem is actually expressed, but as long as you have a bounded region, we'll be able to evaluate the area. So for instance, let's technically take a look at the first problem, and I provided the graph of what this one represents. It's a square root function, and we're going to be evaluating the area from technically the values of 0 to the values of 2. And to find the area, you're simply going to be integrating. Let me rewrite it as x to the 1/2, technically from 0 to 2. And the integral of x to the 1/2, it's going to be x to the 1/2 plus 1 over technically 1/2 plus 1. And then we're going to be applying the limits of integration from 0 to the values of 2. And as we apply the integral, well, the new exponent is going to be 1/2 plus 2 over 2, or technically 3/2. So let me just rewrite it as this happens to be x to the 3/2 divided by technically 3/2, and we're going to be evaluating from 0 to 2. Let me simplify it. So we're going to end up with 2/3 times x to the 3/2 evaluated from 0 to 2, which is going to give us the 2/3 times, well, 2 to the 3/2 minus 2/3 times 0 to the 3/2. The second portion cancels out. So second portion automatically 0. We're still left with the first portion, which is going to give us, in this case, 2/3. And let me flip the exponent so we can find an exact value. So this will be 2 to the 3rd raised to the 1/2, which happens to be 2/3 times 8 raised to the 1/2. And then we can simplify this further. So this will be 2/3 square root of 4 times 2. And we can extract a 2 out. So we're looking at, this is 2/3 times 2 square root of 2, or as a exact value, 4/3 square root of 2. Let me get a decimal approximation. This is approximately 1.8, and let me just keep 3 decimals, 8/6, keeping 3 decimals. And in this case, we can say that the total area under the curve for f of x is equal to the square root of x from x is equal to 0 to x is equal to 2 is is actually exactly 4/3 square root of 2, which is approximately 1.886, and I'll say units technically squared. So that would be our final answer. A lot of our applications are going to represent some physical quantity. So in this case, because they're asking for area, we're going to be expressing it as technically units to the second power. That's actually it for this one. And once again, as long as you have a bounded region, the integral is going to give us the exact area. The exact area for this one ended up being 4/3 square root of 2. Okay, I think we just have enough time to do the second problem without going into another video. And in this case, we're going to be evaluating the integral of the sine function. Our function happens to be bounded between 0 and the values of pi. Now, the integral of technically sine, it's equal to negative cosine of x, and we're going to be evaluating it from 0 to the values of pi. And in this case, let me just keep the negative out. So we're going to be evaluating the values of cosine of pi minus the values of cosine of 0. And in this case, we end up with negative cosine of pi is equal to negative 1 minus the values of cosine of 0 is 1. So we end up with negative, and in this case, this is going to be negative 2, or a total of 2 units. I'll write it out as the total area under the curve for f of x. This is equal to sine of x from x is equal to 0 to x is equal to pi. It's technically 2 units squared. That's actually it. Once again, as long as we happen to have a bounded region, meaning the function is not discontinuous, then all we need to do is evaluate the integral, and that's going to give us the area. Okay, I'm going to stop here. I'll put the other ones on a separate video.